All right, so today we're talking about combined loading examples. Today we're going to talk about combining loads in a way that we actually have to superimpose or add together the effects of the load. So when we do this, there are some important things that must be true in order for us to be able to do this. One of those is that our material must be homogeneous. So that means that E, G, Poisson ratio, all these factors, all of these moduli or material properties have to be consistent throughout the material and regardless of the direction. It has to be linear elastic. So this is stress, that's strain, or it could be G and gamma. But either way, that needs to be a linear relationship between the two. And if we're being more realistic, it's more like this. It needs to be a linear relationship so that when we add these effects together, we can simply add them. So we know if we have some amount of strain and then we add some more strain, we can add those two effects. And this is really important. The point that we're looking at has to be far from discontinuities or applied loads. All of the equations that we have for stress in this class are really kind of average values, if you will, right? Our P over A and our, they're not looking at stress concentrations at around a loading or at a sharp corner or anything like that. So we need to be kind of out in the main body. So for example, if we have this here and we apply our load and our moment, the point that we might be interested in could be somewhere here in the middle, but we don't want to look at something here right at this end where we're applying those loads. Okay, so the procedure that we're going to follow for a combined loading problem is that we're going to want to determine the internal force and moments at a particular location. So at the location of interest, we need to determine the internal force and moments. To do that, we need to start with a plane. So pick the plane. Typically, it's convenient to pick the plane that is perpendicular to the member. So you might take that as your plane, that perpendicular plane. There may be some instances where you want to do something else, but this is definitely the most common choice. The second thing is you need to calculate the equivalent force acting through the centroid. So the centroid of this cross-section here is going to have, say, a normal force. And I probably should not use red as my plane. I'll cut my plane in green. And there might also be a normal force. So these are the resultants. This is the equivalent force system, if you will, of whatever forces are applied to this body. So there might be some other force applied somewhere else, and we're translating it here to this equivalent force at the centroid. And then along with that, there might be some moment about the centroid. In fact, that moment could be so we might have a moment about that axis. Moment about this axis would give us twisting. So you could have 3 moments, right? You could have a moment about any of the X, Y, or Z axes. It's just going to depend on the original loading that you had. And those moments could be from actual applied moments elsewhere, or they could be coming from the fact that when you have a force and you move it to a new location, you need to also apply a moment so that it has the equivalent effect. So once you've figured out the force and the moment acting at a particular cross-section, it's now time to determine the stress components that result from that force and moment. So for example, if you have a normal force, you're going to get a normal stress that is P over A. And if you are dealing with a pressure vessel, say that image that I showed you that had all those forces acting on it also happens to be a pressure vessel, then you're going to have PR over T and PR over 2T. Can you even read that color? Okay, I'm gonna have to. I liked it because it matched the color of my slide, but I think that's easier to read. Okay, so now note that these are two different P's. Capital P is your axial or your normal load. Little p is your pressure. Okay, both of these create normal stress. Then we have shear force. So we might have this rod being sheared at a particular location. So we see this like within bolts. We have bolts where it connects two plates, and those two plates are pulled apart from each other. That puts a shear force into the bolt, and that's the shear. The stress of that is the shear force divided by the area. This is what we call direct shear, and that's what we've been talking about so far in this class. It's where you have a force acting parallel to a plane. We haven't gotten to bending moment yet, but just a little glimpse into the future. When you bend something, it creates a distribution of normal stress that looks like this. So you have tension on one portion and compression on the other portion, and it varies linearly. So we'll get to that after our, either before or after our midterm, depending on when we have our midterm. But it won't be on the midterm. That'll be tested on the final. So we have bending stress that'll give us a normal stress distribution that is a linear distribution. And then we have torsion. We've talked about torsion, right? You have your shear stress. That is, let's see. It's TR over J, is that right? That's good. Okay, and then the other thing that we need to get up here is when we have bending, not only do we have this normal stress, but we also get a shear distribution that we'll talk about that is parabolic. So just a little precursor to the future, bending is going to give us both normal stresses and shear stresses. So the point is, all of these could be happening at the same time. And it's really important to me that you understand that even though in this class we address them with separate chapters and separate lectures and we kind of treat them like they're all separate things, in the real world there's nothing that stops you from combining these loading effects onto that member. And at the end of the day, they all boil down to two things, either normal stress or shear stress. So all of these up here, those are three different types of normal stress that we can create. And down here we have three different types of shear stress, or three different equations for shear stress. And so what you do is you figure out separately what the components of normal and shear stress would be on your little material element, and then you superimpose them. So if you have normal stress on an X face from two different or three different effects, you add up all of those normal stresses. Same thing for your Y face. Your Y face, if it has normal stress components from different effects, those get added together. And then your shear stresses, if you have shear stresses coming from different effects, you add those together. And then you end up with your stress state on that element. Questions? So I just explained what this slide says. Basically, you get your resultant normal stress and your resultant shear stress, and then that gives you what you're going to put onto this little cube. So this little cube might have some tension, possibly some compression, and some shear. The magnitudes of these arrows are from the addition of the corresponding components. But it's important that you don't add things that aren't in the same direction. So if it's a normal stress in the X, it only gets added to other normal stresses in the X. You never add X and Y stresses together. Same thing with shear. You never add a shear stress to a normal stress. Those are, you can think of them as being like completely orthogonal. You don't ever want to mix them together. You ready to try this? All right, so first we'll do an example together, and then I'll give you an in-class assignment. And when I say together, I do mean together because I don't have a solution written out for this. So we're gonna work together on this. So we're determining the vertical normal stress at the mid-height of the bottom. Let's put the word portion in there. At the bottom portion of the tank. So I'm talking about here. So at the mid-height of that bottom portion, what is the vertical normal stress? And let's say that each of these is 3 feet. We have an exterior diameter of 36 inches. We could make this more to scale. If the exterior diameter is 36 inches, I'm gonna say that's 4 feet.
That's like far enough to treat that.
Yeah. So I'm not asking you about the very top or the very bottom. So we're within a region that we would assume our stresses to be independent of the loading. So we have an exterior diameter of 36 inches. We have a thickness. The shell of this is 1/8 inch. There's a pressure inside of 50 psi. The material that the tank is made out of is steel, and that has a density of 0.2904 pounds per inch cubed. And we have a crane trying to pick this up, but it's still attached to the ground. So that's also going to put loading into this tank. Silly. So what do you want to attack first?
Not the
Pressure? Okay, so we'll get the pressure vessel part out of the way. So we know that we're concerned about the vertical direction. So in this case, is that my hoop stress or is that our longitudinal stress? Okay, I heard longitudinal. So that's PR over T or over 2T? 2T. Good. If you ever forget that, just think about what a burst pipe looks like. Have you seen images of burst pipes where they have cracks along the length? Have you ever seen an image of a burst pipe where it cracked this way around the diameter? No. It's because the pressure always causes more normal stress in that hoop direction because the denominator of that fraction is T instead of 2T. So you always see it burst in that direction. All right, PR over 2T. So we have 50 psi. The radius is going to be, so the outside radius would be 18 inches. Then we need to subtract 1/8 of an inch because we want the inside radius. And we're dividing by 2 and we're dividing by the thickness. So what do we get for that stress?
And what is that, 4 feet?
That's the height of each segment of this tank. So the total tank is 12 feet tall.
And 3,575.
PSI? Okay, and I'm gonna, okay, we'll leave that for now. Okay, what else is happening to this tank? The weight. So the tank itself, from its own self-weight, is going to put the tank into compression. You see that? It has to support itself. So we have the density, but we're going to need to figure out what's the volume of the tank above that point. So we'll say, let's see, we'll say the normal stress due to the weight of the tank is going to be the density. Well, first of all, it's going to be force over area. So let's see, we'll say that the force is going to be the density, 2904 pounds per inches cubed. But now that needs to get multiplied by the volume of the tank. So I would say one thing we could do is we could take that top circle and we'll say pi times 36 inches squared over 4. Is that the area of the top? Okay. Plus, now we have the sidewalls. So the area of those sidewalls is going to be pi 36 inches squared minus, is it 35.75? Is that the inside diameter? Okay. Divided by 4. So that's our area, but I didn't leave any room for the fact that that needs to get multiplied by the height. I think I'm gonna have to move that. So plus pi over 4 times 36 squared minus 35.75 squared. Now, so that's the cross-sectional area, needs to get multiplied by the height. So we have 4, 8, 9, 10. 10 feet. Say that's 120 inches.
That first pi times the 36 squared divided by 4, that's the cap.
That is representing the, yeah, the cap.
So you want to multiply by the thickness. That cap
We do, you're right, we do, because it needs to be a volume. Yeah, thank you. Is that what your disapproving look was about?
No, I was thinking, so since it's just the force over the area, we can be able to just say that force times, or the density times the volume, or times the height times the area, and that basically cancel out. But since you have the cap, then you can't.
Yeah, if we neglected the cap, then yes, we wouldn't have to multiply and divide by the area, but this is only going to slightly change the answer. Okay, so now let's see if we've got this. We have our density times, now we have the volume of that cap because it's including the thickness, plus then the cross-sectional area times the height. So good. So that should give us the total force, and then we divide all of that by the area of the tank. So see what you get there.
What are we dividing that by for you?
So all of this weight of the tank is being supported here on this cross-sectional area, right? And so we're dividing it by that area of the tank at that point to figure out what the stress is.
Where did the 120 come from?
That is the height. So 120 is if each segment is 4 feet and we're looking at the bottom or the middle of that bottom segment, then the height above it is 10 feet and it's in inches, so it's 120.
So you have the density times the volume, right?
Yes.
Then that's gravity. Get force.
No, because this density is written in terms of pounds per inches cubed. So it's already in force units. But you're right, sometimes density is in terms of mass, and then you would need to multiply by G.
55.8. And that's PSI?
Yeah.
Okay. And I'm going to put a negative sign here to indicate that it's compression. All right. Is there anything else happening?
What says, what does that mean?
I mean, somebody is trying to pick this up. They've got a crane, they've attached it to the top of the tank, and they start lifting it, not realizing that it hasn't been unfastened from the base.
So it has to have a reaction.
Exactly. So what's going to happen is this force up here, this 500 pounds, is going to, because of the way we're attaching it to that tank, it's going to put the body of the tank into tension. So we can say the stress caused by the crane. This is going to be a tension, so it's positive 500, and we're going to divide it by the cross-sectional area. Okay, and what do we get there?
This is the force from the crane, or the stress from the force from the crane.
Yes.
$35.49.
PSI? All right. Cool. So now we have 3 different normal stresses that are affecting this object, each of which is oriented in the same direction. So this is, say, a material element that is aligned with the vertical and horizontal directions. And what we're interested in is, what is this tension? So remind me again, what were the values that we got for tensions? 35.75 minus 55.8. 35.49. That's what we, yep. So what does that equal? Okay. So that ends up being our actual value of normal stress in that direction. Now, for completeness, this problem would also have PR over T in that other direction, but it shouldn't have any other stresses in that direction. Okay. And nothing in this problem would cause shear. Everything is, all the loading was symmetric, so there wouldn't be any shear caused. Any questions about that procedure? So the first step is we want to look at this example of a pressure vessel. Here we have a propane tank. And I'm looking at an element that's along the exterior of this tank. Doesn't matter exactly where it is, except that it's in the cylindrical portion of the body. And the supports are 1 meter apart, supports labeled A and B. This cylindrical pressure vessel has an outer radius of 0.75 meters. And it has a thickness of 15 millimeters, so we'll call that 0.015 meters. Oops, sorry, that's okay. So we have an error when we install this tank. Whoever's installing it, for some reason, twists the tank 0.1 radians counterclockwise. So somebody standing over here, looking this way, says that point B is rotated counterclockwise 0.1 radians with respect to point A. And then they set it down and they bolted it into place. And so now that twist is stuck in the body of this tank. So we'll say that the rotation of B with respect to A is 0.1 radians. And we want to determine the complete stress state for this element that we've drawn on the exterior of the tank. And we know that the pressure inside the tank is 8 megapascals. And we know the material, so we know that the G is 27 gigapascals. Where do you think we should begin? What do we need to find? I'm sorry, what was that?
We should section the member to find internal forces.
Okay, so we can look at sectioning this member, and in particular, we're going to want to take a section of the member that's a vertical section to expose normal and shear stresses acting on that vertical plane. And we're going to want to take another section that is a horizontal section to expose any normal shear forces acting in the other direction. Yes, yeah. I can see why you're confused based on the way it's drawn, but yes, that is the bottom half of that tank. Should look. That probably looks slightly better. All right, so on the left-hand figure, we know that we're going to have some normal stresses acting like so. And what do we call these normal stresses? Sigma what? Perfect, thank you. And the other figure with the horizontal cut? Question? Yes, thank you. That is sigma theta. And let me just erase them from the end cap portion just for clarity. We're just looking at the middle part of this body. But yes, we have what we call sigma theta acting in the other direction. So those two stresses are coming from the fact that this is acting as a pressure vessel. But now we need to think about what is happening due to that twist. It's going to add a shear stress, yes. And in particular, which component of shear stress? Tau, what are the subscripts? Did you say theta z? All right, tau theta z. Okay, so here we have, when we take the vertical cut, this surface that we've exposed is a z pointing surface. And so we're going to show on that surface stress components in the theta direction. And we know that the direction that they must point has to be this counterclockwise direction. Because if we're looking at it from where this stick figure is drawn, and we're twisting B counterclockwise relative to A, the shear stress must be going in that direction in order to cause that direction of rotation. Yes?
Should it be the first one that's going? What direction is it going on the second one? Which direction is it?
Yes. So technically speaking, the answer to your question is yes, in terms of which order we write these subscripts. But because we mathematically showed that the two are equal to each other, so we showed that tau z theta is equal to tau theta v, we often get somewhat lazy with our subscripts or just put them in alphabetical order. Okay. Okay, perfect. It's a little bit harder to see or to think about, but technically speaking, we also have shear stresses on this other plane. Because if we have tau theta z, then we have tau z theta. And this is now a theta surface over here in this diagram. So we're also going to have stresses that are going to be acting on this surface as well. But these ones, this image is a little bit easier, at least for me, to visualize it because I know that the torque is going around the circumference, and so it's easy to visualize that I have those shear stresses running around the circumference. But technically speaking, you also would have them on this other cut because those would be, when you look at your little cube, you're going to have the shear stresses acting like that on all four sides, right? All right, so let's see, mathematically speaking, how do we calculate sigma z? Yeah, I mean, generally speaking, it's our force over our area, but specifically we have PR over 2t. Okay, and what about sigma theta? Perfect, PR over t, so it's twice sigma z. So we have all these values we can plug in. We have 8 megapascals times the radius, which is 0.75 minus 0.015. Why am I subtracting? Right, we want the inner radius. Now mathematically you're going to see it's very little difference, but technically speaking we want the inside radius. Divide by 2 times 0.015. Same thing here, 8 megapascals, 0.75 minus 0.015, divided by 0.015. Okay, that gives us, I believe this one is 196 megapascals. And sigma theta must be double that. So that would be 392. All right, so that's the first part. That's our normal stress. The second part is looking at the torsion that's due to that rotation. How do we get from the rotation to the shear stress? Can we go directly, or do we need an intermediate step? We do need to know J. Yep, that's one of the things we need to figure out. So we could start with that. So J should be pi over 2 times 0.75 to the fourth minus 0.735 to the fourth. Does anyone have a calculator out? Can you give us a number for that? So while they're calculating that, what are we going to do with this J value? Once we have it. Okay, so you're saying that the shear stress equals TR over J? What's that?
J times G, right?
That's not this equation. There is an equation with JG. What equation is that? Yes, the angle of rotation. So delta theta equals,
TL.
perfect. So we have two equations here. We know our rotation, our change in rotation. We know the length, we know G, and we know J. Then we can back solve for the torque. Once we know the torque, we can plug that in over here with R and J, and we can get the shear stress, which is what we really want. So do we have a value for J?
0.0386.
0.0386, perfect. Okay, so we can say that delta phi, actually we need to plug in a number for that. This should be 0.1 equals T times 1 meter. And remember, this is 0.1 radians. If we were given the answer in degrees, we'd need to convert that to radians. Then we divide by GJ. G is 27 gigapascals, which was given in the problem, and we computed J to be 0.0386. So now the units on that are going to have to be meters to the fourth. So this tells us that the torque is 104,176 kilonewton meter. I plug that into the shear equation. And what does that give us for our final answer?
I get like 1,983,662.
What's after the 3?
662.
Is anyone able to confirm that? Did you get? Okay. J does cancel out. So if you want, you can solve for T in terms of the variables, plug them into the other equation, and you'll see that J does cancel out. So you could have short-circuited that step. All right, so this gives you 1.984 megapascals. This is kilopascals. Okay. All right, so now we have our stress components. And it's important, I want to point out that if we go back to the previous slide, we have two distinct normal stresses. And yet, even though we have two shear stresses showing up, we know that they're equal and opposite magnitude, or not opposite, they're equal magnitude because they're just an expression of the same stress acting on the two sides. So we don't need to solve for any additional stresses. So we have our 3 values. So if we look at this cube of material, we know that we have the normal stress in the Z direction, which is going to be a tensile stress. So that is 196 megapascals. We have a tensile stress going around the hoop direction. That's 392 megapascals. And then the last is the shear stress. And we said that was 1.98 megapascals. I think perhaps the trickiest part of the shear stress is knowing what direction you need to place the shear stress, whether I have the arrows drawn properly or whether I need to flip the direction. So one thing you want to think about, or there's a couple different ways that you can think about it. One is that if you have, say, this section cut, or say that's point A and that's point B, and we know that the torsion must be going in that direction because that's how you get the counterclockwise rotation of B relative to A. On this near side, that torsion creates a shear stress that goes in the same direction as the torsion. It's then resisted by the reaction, which would be on the back side. So you could cut a second cut, really at any plane through here, and it could even be, so this side here is that second plane that I would be cutting, and this front side, or this right side, would be the first cut, the cut near me, where I'm showing that torsion, creating an applied stress onto the material, and then the reaction is what's holding that material onto the rest of the material, and it's going to be going in the opposite direction. So you're going to get this reaction to that applied stress on the backside. The other way you can think about it is that the direction of these arrows is going to govern the deformation of that shape. So with the arrows shown the way they are, it's going to, let's see if I can draw this properly. No, I definitely can't. But we'll try one more time. It's going to do something like that. You can see the way that those arrows are, they're going to push those corners out where the heads of the arrows are pointing. And so you can think about how these elements along the exterior of a circular shaft should deform. So if point A is back here by my left hand, and point B is up front, and point B is rotating counterclockwise relative to point A, so it's twisting like this, you can see the direction that those are squeezing. So you can see this corner here and that corner there are becoming more acute. These two are becoming more obtuse, which means the arrows must be pointing towards this corner and that corner. And so that means this front side is pointing the way that I'm rotating, pointing the way I'm applying that force, and then the back side is going the other way. Questions? Okay, I have an example now that you're going to try as an in-class assignment. So here we have a screwdriver, and at this plane where it's interfacing with the wall, so here we have this plane where the screwdriver is intersecting the wall. The cross-section of the screwdriver at that point looks like the circle inside of that box. And we're interested in point A, which is a point at the very top of the screwdriver. Because it's pushed up against this wall and trying to twist, there is a torque applied of 20 Newton meters. So that is this torque here. And it's a little bit difficult to see, but that torque is going, if you were to put your fingers in the direction of that torque, your thumb would be pointing in the positive X direction, which in this case is to the left. And with our hand, not only are we pushing towards the wall with 120 newtons, we're also using our wrist to apply a 15 Newton meter moment. Because the idea is that, how many of you have ever used a screwdriver? Okay. What happens if you just push straight on that handle? Try it again. Go home and try it again. Yeah. Work on this example, and then we'll talk about it a little bit more, and you'll see mathematically. Okay, let's go ahead and look at the solution for this. So we have this applied torque, the 20 Newton meters, about the x-axis, and there are no other moments about the x-axis. Because that x-axis is along the length of that shaft, we know that's going to act as a torsion. That moment is going to be twisting about the longitudinal axis. So we can say that our shear stress is TR over J, where we're going to use the full radius because we're interested in point A, which is on the exterior of that shaft. So we have 20 Newton meters times 0.005 meters divided by, this is pi over 2 times 0.005 to the fourth. And what does that give you?
No, 1.1 or 101.9 MPa.
Yeah, it should be 101.9 megapascals. All right, so then the question is, well, what do we do with these other forces and stresses? Or sorry, forces and moments. Perfect, so we want to move them to the point that we're interested in. In particular, we need to move the force to the centroid of the cross-section, not to point A, but to the centroid of the cross-section. So I need to move that force here, so I'm gonna put my 120 Newton force. But if I move that force, I need to add a 120 Newton force in the opposite direction so that I'm essentially adding 0 to this system. Now this 120 Newton and that 120 Newton, in terms of the sum of the forces, they cancel, but in terms of moments, they get replaced with this. They act as a couple and they get replaced with this moment, which is 120 newtons times 0.125 meters.
Do you have to move it another 5 millimeters going to A?
No, you always want the sum of the forces at the centroid.
Gotcha.
Yeah. And then we assume that the distribution of those normal forces is uniform throughout. So we can get the actual stress at A by taking, so we take the stress in that x direction by taking the 120 newtons dividing by pi 0.005 squared. And that we're assuming that's a uniform value for any point on that plane. Okay, so now, coincidentally, this 120 times 0.125 should be equal an opposite direction as the applied 15 Newton meters, so those are going to cancel out. So you actually have no moment about that z-axis, which is good because that would require you to treat that drill bit as a beam, and we don't know the equations yet for that. So we're going to ignore that for the moment. Or not ignore it, but it's going to go to 0 for the moment. All right, so now...
So why is it going to 0?
Because the couple, when we moved that 120 Newton force to the centroid, it created a couple that was equal to 120 times 0.125 meters, which is 15. And it's the opposite direction as this 15, so therefore they sum to 0. Okay, and we calculate this here, and what does that give you for your normal stress?
1.5.
Okay, is that what others got, 1.5?
Yeah.
Perfect. Okay, so then the last step is you need to draw this on an element. You can either draw a 2D element if you'd like, where this is x and that is z. We're looking at the top down at point A. Point A would be right here in the middle. Or, what's that? We're looking at the top down. Yeah, y is coming up at us, or coming out at us. Or if you'd like, you could draw a cube where this is x, that is z, and that is y. So it's up to you how you want to draw it, 2D or 3D. But we know we're going to have this compressive stress. That's going to be the 1.5 megapascal. So even though we got a positive number, you know that it is compression. And then you have your shear stress. So once again, you have to figure out what direction that shear stress is acting. If I'm looking at this, right-hand side to this side, should I draw that arrow up or down? I have one vote for down.
No. Oh, yes.
I'm cutting. I cut the screw right
There you
here.
go.
The last cylinder.
Okay, I've got a few more for up. Okay, so you're looking at it from the wrong direction. So this I can't change what you're looking at, but that element that I've drawn is acting at the top here. And so because the torque is twisting this direction, which is the clockwise direction, the side of that element that's closest to the screwdriver needs to be going in that same direction, and the back side would be going in the opposite direction. So the back side would go in this direction, and then the other two follow suit. Now, if you want to draw it on the 3D element, now your normal stresses look like this. So that'd be your 1.5. Let's see, these over here need to be 101.5. Now your other stresses need to be on the Z and the X faces. So they need to go like this and like that.
How do you know which plane to look at it from? Like, why wouldn't you look at it from the YZ plane?
Because point A is on, okay, so because point A is on the top.
So if you sliced it right there, wouldn't it be technically right at the corner? So it would be on top and that side.
I want to look at an element that is along the surface. So I'm not, let's see. Yeah, I want to be looking at the exterior.
But if we just rotated A down to G, it would be at the same spot that it was at on the cylinder that we just looked at in the last example. And we looked at, okay.
So if I'm looking at point B, then I would look at an XY plane. That's okay.
So I have a question.
Yeah.
If, like, say you're like halfway in between A and B, like 45 degrees rotated,
Mm-hmm.
is there like a equal component?
Yeah, so if I were, say, at this point here,
Yeah.
I would probably draw it in, I would abandon my XY at that point, and I would go to an R theta Z system, and I would look at the R theta Z, because that's really what I'm doing at A and B, is I'm looking at an R theta Z system, except that it superimposes to this X, Y, and Z that exists.
You want to see down the exam.
Oh, you certainly could. I mean, it really doesn't matter where the point is, because if it's a circle, it's all the same. One, you could either turn your coordinate system however you want it. If I don't give you a coordinate system, you can make your own, or just always use the R theta Z. That works great too. Anything else? Okay, so going back to, a lot of you, or some of you, struggled with the forces that are applied here. We're arguing over how you actually hold a screwdriver. So the thing is, if you just had that horizontal force and you don't have your wrist kind of applying a moment, there's going to be a net moment acting at this drill bit. And so that's okay as long as there's something to resist that moment. But oftentimes what's going to happen is that screwdriver is going to slip out of the head of the screw that you're screwing, because the thing that you're relying on to resist that moment is that little bit of a connection between the bit and that screw, and it has a tendency to want to go like that. So you can maybe apply a small moment, but if you're applying too much force, it's going to slip. So then if you're going to apply a lot of force, you need to kind of torque your wrist a little bit, or apply a force that's kind of upward and over, so that unwittingly you've applied moment. Because if you have a force that is, say, pointed like this, that really translates into two different components, one of which is vertical and one is horizontal. This one creates a moment that goes like that. This one creates a moment that goes like that. And one of those needs to be bigger than the other. Does that kind of make sense? Yeah. Oh, that's not what I want to show. Okay, so one more example. You're not going to do this one as an in-class assignment. I'll just go through it real quick. What I want you to see here is the idea that now we could actually have different forces causing stress components in the same direction. Because the two problems that we've done so far, we have different forces acting, but each of them creates a force in a different direction. So either a different normal stress or only one created a shear stress. We never really had to superimpose them. Instead, we just overlaid them on one cube, but never had to add numbers together. So in this case, what I have is I have three different pressure vessels. Each one has a 50 psi pressure. And for some reason, I've decided to stack them. They're flat. And so the weight we're presuming is distributed around the circumference. And each of these weighs 1,000 pounds. Each tank weighs 1,000 pounds. So that means I have 1,000, 2,000. And if I'm looking at the cross section that's right at the middle of the bottom tank, I have another 500 pounds that's all acting downward on that cross section. But then I also have the pressure of that tank acting as a pressure vessel. So in this case, we'll say this is our, say that's our Z direction. So we're going to have a normal stress due to the weight that is going to be the 2,500 divided by that cross-sectional area of the bottom or of the tank. So if I have 36-inch diameter, that means I have an 18-inch radius. Thank you. So pi r squared, and then minus pi r squared of the inside. So let's see, what is that? That would be 18 minus 1/8, so 17.88
or 875.
Perfect. Okay, so that would be our force over our area. And so this is due to axial load. Then I have the pressure vessel. So the pressure vessel also gives me a sigma Z. And that is PR over 2T. So that would be 50 PSI. Times 17.875. And divided by 2 times 1/8. Okay, can we get a value for that?
Uh, 3,579.
2,500. You're right. Yeah. I just asked about the vertical normal stress. You could do sigma theta, but that's not the superimposed part. Thank you. And I didn't write down what you said for some reason. What was this one?
Oh, you did. It's right there. Oh, the 3,575.
No, for the first one, for the top one.
The top one.
Maybe I forgot to ask that to be calculated.
Yeah. Okay. 177.455.
Okay, 177.5.
Sure.
Okay, so what we're saying is that due to the weight of the tanks, we're going to have a compressive stress. And that compressive stress is the 177.5. And due to the pressure of the tank, we're going to have a tensile stress, which is 3,575. Yeah, these should all be PSI. Those are normal stresses acting in the same direction, so we can add them together. And then the net is what the material is actually seeing. So the net is going to be a tensile stress because that is the larger of the two values. So we get 3,000. Am I close?
You said.
Mm-hmm. Did you get something, Eddie? Should be a small, one of these should be negative, right? If you have compressive, that should be a negative stress. So the net result should be smaller than this tension stress.
397.5.
What'd you say?
397.5.
3397.5. Okay, perfect.
So which one did you assume to be negative?
Compression is always assumed to be negative. Yeah, so this one here will be negative. So the weight is causing a compressive stress because that weight is acting down. The reaction is then going to be going back up, so you're squishing the material. The pressure vessel is trying to push outward, or the pressure is trying to push outward, so that's always putting a tension. So we have positive tension from the pressure vessel, negative compression from the weight. You add those two together, so it's 3575 minus 177.5, and your net is 3397.5. You could also see this with shear stress, and we will as we get more into beams, but you could superimpose shear stresses or normal stresses anytime you have them acting in the same plane on the same direction. Questions? All right, then let's take a sneak peek at the topic that we're going to cover next time we meet. And next time we meet will be the last bit of material that will be on the midterm. So everything through Wednesday will be on your midterm when we come back on Monday.
Yes.
The Monday after spring break.
That's sweet. That's always that's not very nice.
But our homework got pushed back, so we have 2 days less to study this material than the other class. Right, we would have 2 days, if the homework got pushed back, we would have 2 days less on the test too, right? Study the material. Push our homework back.
No, because the lecture schedule, yeah, no, the lecture schedule is the same. You have the same amount of time.
Hey, I tried.
Okay. Question, Albert? Or David? Okay, for your project?
Yeah.
Okay.
Is that your Blackboard or is that turn in?
Yes, it should be Blackboard. Do I have a link up for you to submit it?
I haven't checked.
Okay, I can check as well, but yes, it should be through Blackboard. All right, so okay, so just a real quick reminder, what's the difference between maximum shear stress and absolute maximum shear stress? Okay, so we could have 3 Mohr circles, and the absolute is on the biggest of the 3. Now, what do those 3 Mohr circles represent? Rotation about different axes, so they're different planes within the material. Exactly. So the idea is that when we're talking about in-plane shear stress, if we're just talking about rotating in one plane, we can calculate a maximum value of shear. But if we allow ourselves to rotate it in any direction about any plane, there is one such orientation in which we get the absolute maximum shear stress, which is the largest of any of those planes. Good. Okay, so that is going to become, the topic of absolute shear stress is going to be very integral to our failure theories. So today we're talking about initial yield and failure theories, and we'll continue that on Wednesday. Failure theory. So how we determine whether something has failed. And we're going to be looking in this class exclusively at yielding. So we're considering yielding to represent failure. 10. This is chapter 10. We did. With chapter 10 is where we learned stress transformations, and now we're going back to learn about failure theories. Okay, so large deformations, or yielding is defined as large deformations with relatively small increase in applied load. So if we look at, say, a stress-strain curve, it may start with a linear segment and then kind of bend over like so. And so in this plastic region, this region here, there's very little increase in strength for the large amount of elongation that you're getting. And that's what we call yielding. Yielding is caused by the slippage of molecules along oblique surfaces due to shear stress. That's a mouthful, but let me draw a little picture. So if you have a material and it's being acted on by some tension, what I'm saying is that there's an oblique plane like this in which you have shear stress occurring. So even though you're only applying normal stress, your maximum shear stress is on this 45-degree plane. And really any plane in between 0 and 45 is experiencing some level of shear stress, with the maximum being on the 45. And because there's shear stress on that plane, it's causing molecules to slip past each other. If this is not permissible for the type of material you have, it will fracture, and that will be a brittle fracture. But if it's a ductile material, it will allow the molecules to slide past one another, and they're going to kind of rearrange. And we talked about that a little bit when we talked about strain hardening. It was the idea that molecules in the material were sliding past each other when they were yielding, and then they kind of interlocked. In some materials, they would interlock again and then be able to endure more stress. Okay, so once yielding occurs, Hooke's law no longer applies. If you had a linear elastic material, you could use Hooke's law in this region where the slope is E, but after it stops being linear, or after it changes its slope, you can no longer use that equation of stress and strain being Hooke's law. So typically we consider this to be a failure. We don't necessarily want it to go beyond yielding. So when we have uniaxial stress, so when we apply just one stress, say, like I said, we have our material and we apply tension to it. When the stress in that material, because we only have one value of stress, so when that stress equals the yield stress, so when F over A, this is F, when F over A equals the yield stress, we say that material yields. And for uniaxial loading, that's fairly straightforward. But it becomes a lot more complex when you have biaxial yielding, because what you'll see is that we might actually have yielding occur before any of the stress components reach yield stress. So in the uniaxial situation, yeah.
Why would that happen?
The question is, why would that happen? And I don't want to answer that because we're going to get there. We're going to get there. We'll talk about it. But the general answer is that the overall stress state is such that it causes yielding to occur, even though no one component is equal to the yield stress. So we have, in this uniaxial direction, we determine our yield stress from the tensile testing, and we can use either the lower yield point or the 0.2% offset method. So you should remember that if you have a stress strain curve that looks something like this, you can either use this value here, which would be that lower yield point, or you can do the 0.2% offset and get some other estimate, which would be relatively close in terms of estimating your yield strength. So when we have this uniaxial stress state, we only have one non-zero stress. All the others are zero. So we say that when that stress equals yield stress, we've yielded. So one of the ways that we can predict stress is through what we call the Tresca yield criterion, and this is also called the maximum shear stress criterion. But this is just one of a few different ways that we predict yield. And so the rule, or what guides this theory, is that a material under a multi-axial stress state will yield when its maximum shear stress reaches the value of maximum shear stress that occurs in a uniaxially loaded material at yield. So to kind of answer your question, first of all, there's different theories, and so each theory will have a different reason why yielding occurs. But in this theory, what it's saying is that a material can withstand a certain amount of absolute maximum shear stress. And so regardless of whether that occurs in a uniaxial sense or a multi-axial load application, that material, because the material doesn't really care how you're applying the loads, it doesn't know. All it knows is what is it experiencing on an element within that material. And so it's not necessarily that there's something magical about yield stress, so much as there's a maximum shear stress that is occurring. So let me restate. So I have this material and I apply a yield stress. That yield capacity, that normal stress, yield stress, is not actually maybe that, let me see. It's not necessarily what's causing it to fail. It's not failing because the normal stress is larger than the yield stress. We say that, but that's not actually what's happening. What's happening is that there's some maximum shear stress along this 45-degree plane, and that's what's causing it to yield, is that maximum shear stress is being exceeded. But it always, because you can relate these stresses, you can always relate it back to what that normal stress is, right? Because you can rotate from this 45-degree element that's experiencing the maximum shear stress to this vertical and horizontal element that's experiencing the maximum normal stress. So, but it's actually that, according to Tresca, it's actually that maximum shear stress that is governing yield. And so we have some value in a uniaxial test. So in a uniaxial test, we have one of our stresses equal to the yield stress at the time that it starts yielding. The other two normal stresses are equal to 0. Therefore, our absolute maximum shear stress is sigma y over 2, right? If you take 1/2 sigma A minus sigma C, it ends up being 1/2 sigma y. So this is the magnitude of your absolute maximum shear stress at yield of a uniaxially loaded material. And we're saying that's what causes failure, is reaching that shear stress. So when you come into a multi-axial shear stress, you could have any values of sigma for sigma A, B, and C, right? Absolutely any values. Whatever loading you apply, you get some principal stresses, A, B, and C. So then you could compute 1/2 sigma A minus sigma C. And when that value reaches sigma y over 2, you would expect yielding to occur. Any questions? Okay, so we will pick up there next time.